Here's another torque and static equilibrium example that we'll call the hanging platform example. So let's say we have the following. We have a board that is held up by ropes on either end. So we'll label these rope 1 and rope 2. Sometimes in textbooks this is given as like the window washer scaffold, but can't remember the last time I saw a window washer on a platform, but I guess it probably still happens. Anyway, okay, so this platform is uniform and has a mass of 10 kilograms. It is 2 meters long, and on it there is an 8 kilogram box that is 0.7 meters from the edge. Okay. Other problems, we could add a person on here too. We'll just keep it to just the one box. So, what are the tensions in the two ropes? And they do not have to be the same, and in fact, we will be able to show that the tensions in these two ropes are definitely not the same. Okay, so we're going to start by drawing our extended free body diagram under this. So our free body diagram, we draw our object as a line. Our forces are points on this line. So what forces do we have on this? Well, we have two ropes attached to it, so those are easy. We'll call that force 1 and force 2. We're assuming these are perpendicular. If it wasn't totally clear from the diagram, you should ask, but we're assuming that those are perpendicular here. We have this 8 kilogram box pushing down on this. We'll call that F box. And we have the weight of this platform itself, which we will call F gravity. Okay, so we know some of these distances. We know this distance is 0.7 meters. We can label these on the free body diagram since we'll want to know what those distances are. Where is this force of gravity acting on the board? Well, it is uniform thickness, which tells us the center of mass is in the middle, which means this distance is half of the 2 meter length of the board, so that is 1 meter, which leaves this as 0.3 meters, and now we know where everything is. All right, I'm going to erase our picture since we are ready to solve the problem. Okay, so if the system is in equilibrium, we could think about this in terms of Newton's laws, right? So for equilibrium problems like this, we know it's always true that the sum of our forces is equal to 0 and the sum of our torques is also equal to 0. This is just always true. Now, let's look at the sum of the forces. So we have two forces up, F1 and F2, and two forces down, Fg and F box. I should say, we know enough to know how big these are, right? F box is equal to, 8 kilograms times 9.8, which is 78.4 newtons. So this is 78.4 newtons. The force of gravity on the platform, that is 10 kilograms times 9.8, so that's 98 newtons. So we could write down an equation with our sum of forces that would look like this. Our sum of our forces is force 1 and force 2, the forces of the two ropes up, minus 78.4 minus 98 equals 0. And that is as far as we would be able to get in chapter 4. We would know that force 1 plus force 2 would have to add up to the weight of this 18 kilograms total, but it wouldn't tell us how much is in each of the ropes. So that does not get us very far. Okay, so we're going to use these, we're going to use torque. We're going to use the sum of our torques is equal to 0. And this has to be true for any point that we pick. So we literally can pick any point here and get our way to a solution. But I'm going to pick this point at the left end first to show you what happens. Okay, so if we're using this as our rotation point, all of our r's in our tau equals r f perpendicular equation, all of our r's are measured from this point, right? So our torques, the sum of our torques is going to look like this. Torque 1 plus torque gravity plus torque box plus torque 2. So going through these in order, torque 1, so we're doing this just from left to right, torque 1 is equal to R times F1. Well, R for F1 is 0, right? This is right at this point. So 0 times F1 is just going to be 0. The torque from gravity is going to be 1 meter times our 98 newtons of torque. 98 newtons of force to give 98 newton meters of torque. I made a tiny mistake here, sorry. This gravity force acting downward on this end relative to this left pivot point is going to act to rotate things clockwise, right? Which means this is the kind of torque that should have a minus sign in front of it. And the same goes for the torque from the box. So this should also be a minus sign. This distance is 1.3 meters. And this force is 78 newtons, or 8 times 9.8 newtons. Finally, we have force 2. Now this one is positive, it is counterclockwise, and that's 2 meters away. So we have plus 2 times force 2. And all of those added together equals 0. Okay, I'm going to clear some room. So we have 0, we have minus 98, we have minus 1.3 times 78.4 plus 2 times F2. So if we solve for force 2 in terms of this stuff, we get, we can add these to the other side since this is all equal to 0 because our sum of the torques is equal to 0. So force 2 is equal to 98 plus 1.3 times 78.4 over 2. And that is equal to 100 newtons of force. So we have 100 newtons of force tension in F2, and that is it. So this is one of our answers, right? We're trying to find what those two forces are. So we get F2 equals 100 newtons. This is a big deal. The fact that we chose this one at the left made F1 disappear from our equation and only left us with one thing that we didn't know. So that turned out to be a very convenient choice to make. If we had picked some other point, we would have gotten an equation that was correct, but it still would have F1 and F2 in it. Now, that equation with F1 and F2 in it could be combined with our equation that we wrote a little while ago for the sum of the forces, and give us two equations with two unknowns, and we could solve that system of equations for F1 and F2. That definitely works, but it is this way is shorter, right? We didn't have to solve a system of equations, we just solved the algebra here for F2. So picking your point, in these sorts of problems isn't about getting the right or wrong answer. It's just about making it fewer steps between you and the answer. So picking the right choice of points so that one of the unknown forces goes away, leaving you with what you want can save a lot of time. Okay, so let's do the same thing, but instead of picking the left end, let's pick the right end. So we'll pick this end as our rotation point. So by now you should be able to guess what's going to happen. If I pick this point as my rotation point, I'm going to end up with a torque equation that has a torque for F1, it has a torque for gravity, it has a torque for the force from the box, but it does not have a torque from F2 because R is equal to 0 for F2 if we pick this point. So that's going to again leave us with an equation with only one thing we don't know, F1, which is the other piece we're trying to solve for. So let's go ahead and do that. The sum of our torques around this right end is now equal to, so we'll start with F1. What am I doing? The sum of our torques is equal to 2 meters times F1. And this is, around this point, force 1 would give us a clockwise turn, so this also needs a minus sign. Now we have gravity, which is 1 meter away and is still 98 newtons. So we have 1 times 98 newtons. And now this notice, around this point, gravity pushing down is a counterclockwise rotation. So this is positive. So even though when we picked this other point, gravity gave us a negative torque, when we pick this point, gravity gives us a positive torque. So there isn't anything, the fact that gravity is down is not enough to tell us whether the torque is positive or negative. It depends which side our point is on. So you really have to, when you're changing your rotation point, you really do have to think about whether it's positive or negative every single time. That's just how it goes. Okay, we also have the force from this box. That is also going to be a counterclockwise positive torque. That distance is 0.7, and that is still 78.4 newtons. And the sum of the torques is equal to 0. I guess I don't need my units there because I haven't written units anywhere else. All right, so now we have an equation where F1 is the only thing we don't know, so we can solve for that. We will do that up here. So F1 is equal to 98 plus 0.7 times 78.4 over 2, and this is equal to 76.4 newtons. So those are our answers to the question. We're done. We can now check our answer. We don't have to, but we might as well. So we know we have, let's erase this. That's okay, yeah. We know we have, well, let's look at our sum of forces equation, sorry. So the sum of our forces was equal to F1 plus F2 minus 98 minus 78.4. Right, these were our two weights down here. So minus 98 minus 78.4 is equal to minus 176.4. Force 1 is equal to 76.4, and force 2 is equal to 100. So we have 76.4 plus 100 minus 176.4. That indeed does equal 0. So that is good. That's our check on the answer. The total weight that those ropes are holding up is exactly the same as the total force the two of them are feeling combined. All right, so this is a good, well-rounded static equilibrium problem. The only further complication we can add is if these ropes or other forces are at different angles, and that doesn't change any of the problem solving, except in our torque equations, it's going to add, we have to add some trigonometry to find what component is perpendicular, or maybe we use the RF sine theta equation, so we get some sine thetas. But in terms of the like problem solving steps and the diagrams and stuff like that, even more complicated problems are all going to follow basically this exact same recipe.